programming. That's kind of the name of the playlist where I keep functional programming stuff. So this is now already 21st, I don't know, 20 or 21st of Lambda calculus. This will be a short session. I have some time, so I'd like to have a look at natural numbers. Now, so far I've done and, or, and booleans, and I've done that kind of in a refreshing kind of a way for the last 2 or 3 times, and frankly it's still kind of blurry. Now, what I was thinking, should I go, that's the thing, like how long do I want to be stuck at this? Sometimes it's helpful to move on, and what I learn I can apply, and maybe that will help in the what I've learned previously. Yes. So, false, true, false, true. I have to respond to something. So yeah. Yeah. So the or, false, and cond, and make pair, and first and select second. Really tricky, really tricky. Really tricky, really tricky. So I'm not sure if it will be helpful to go to natural numbers. Maybe, I think maybe it will, because this, it's still before the recursion, drops by. So it might be helpful actually to do the numbers as well, since select first are used as well. And then maybe go back to the booleans. I'm actually not sure. I think I will try and then come back, because we have here the cond and the predicate, and basically just this seems to be just an extra layer of abstraction. So I think the bigger leap of abstraction was the booleans, where this kind of constant substitution and then renaming of the functions has been introduced. This is basically still on the same level, except we have numbers and certain kinds of predicates, simplified notation. We now rewrite all our definitions, and then all the definitions will be rewritten, which is also kind of nice. For some functions, there are standard equivalent notations, right, and summary. So I think it will be kind of maybe good to go up to the summary, where the exercises come. Where's the implication and the equivalence, and then comes the recursion and arithmetic. So recursion will be very interesting. This is basically where programming begins. I guess you could say that, right? No, maybe not. Summary, free variables, normal order, met the lambda calculus, or maybe I should just again basically read the whole thing from the beginning. I think conditions, boolean, and integers. I feel this series is going to be very long. So we have conditions, booleans, and integers. So that was the third chapter, right? With not, and then or. And now natural numbers. Maybe to read it up to the end, so up to the fourth chapter, and then read the whole book again. I'm kind of ready to do that. It's just, it will probably take so much time. Then I was trying to somehow, so let me go to cd code Lambda. So sure enough, I have the Nix REPL, right? The Nix REPL is kind of nice because I can use this style of writing, lambdas, almost like with how they write it with a dot, only I have two dots. Yeah. Right. Or even like this. These are all lambda functions, right? And this is very nice. Well, I'll just start reading about numbers, okay? This will be probably a more relaxing kind of a session where I simply read. Natural numbers. We tend to take numbers for granted in programming. that's kind of true. But we now have to consider how to represent them explicitly. Our approach will be based on the ability to define natural numbers, non-negative integers, as successors of 0. Now, as far as I know, the suk, the successor, is something, right? Some kind of a lambda head, and then that thing plus 1. This would be the successor function. Of course, you would have to define the 0, right? But basically, you can now create numbers because it's always something. So 0 basically is successor. Well, 0 is 0 basically. So if I do 0, I get a 0. 1 is successor of 0. Right? So if I write 1, I get a 1. 2 is successor. 2 is successor of 1, right? But you could say, let's just reuse the 0. So you could say successor of 0. And 3 is successor of 0. So now basically we have 1, 2, 3, and so on. That's as far as I know. This is how you would define these numbers, right? Maybe this is too loud. Now I'm curious what's going to happen here. So 1 is the, okay, 1 is the successor of 0. Yes. 2 is the successor of 1, or the successor of 0. 3 is the successor of 2, or the successor of 1, or the successor of 0, successor of. I think if you repeat it too much, you'll get a beat or something. Successor of. Okay. Thus, the definition of an arbitrary integer will be that number of successors of 0. Yeah, so 3 is the 3 successors of 0. 2 is 2 successors of 0. Okay, and so we need to find a function 0 to represent 0, and a successor function suk, so that we can define 1 suck 0 1 suk. Okay, 1 successor 0, 2 is successor 1. I think I want to go back to my Alka crab. Yeah. "30 Fantasy Open World Ambient Tracks, Alka Crab. No copyright. Really nice stuff. Check it out. So, thus the definition of an arbitrary integer will be that number of successors of 0. We need to find the function 0 to represent 0 and the successor function suck, so that we can define def1 suck 0, def2 suck 1, def3 successor 2, and so on. Right, I kind of did that here, but I didn't use really lambdas. Or I did. Note that 2 is equal to successor of 0, and 3 is equal to successor of 1. Successor of 0, okay, and so on. That's what we did, right? So there are a variety of ways of representing 0 and successor. We will use definition of 0 equals identity. Oh, this is not what I did. So he's writing that 0 is identity. But how is a 0 identity? Because the identity itself, maybe this is just temporary because it's it's kind of weird because identity has this, it's almost like a type, it's like an polymorphic, right? Type A. So this can be anything. You could do identity boo boo and you can get back a boo boo. So how is that a zero? Or maybe he's actually not, no, he's actually using the mathematical definition. Right. So the zero is the identity in addition of numbers. The zero is the identity. That's the mathematical idea. Right. He's not, I don't think he's reusing. Well, only if he's doing it like this, I guess. But how would he how would we know that we will only supply a number to the identity? So the each, like, I think I'm not good actually at explaining this. It's abstract math, right? So I think it's called like a monoid. Is that a monoid? Like you have the identity and a binary operation, and that makes a monoid. Not sure. I forgot that. I saw many videos about that and read about that, but I kind of, I can't really explain it. But the operation of identity is important because it's the zero. So let's say you add a zero to a number, right? If I add a zero to a number, what do I get back? I get back that same number. So it works like the identity function. That's the identity because whatever I give to 5, I'm going to get a different number. Whatever I do to 5, I'm going to get a different result, except if I give it a 0. That's why this is the identity. It almost like identifies the number as the number. You might say, right, I'm already adding to 5. I know that, so why? But it's still different. It's almost like I don't know what you're giving it to me, but if I add a 0 to that number, it will be the same number. Right, anyway, let's see what he will do. So, definition of 0. Identity. So if I do now 0, yeah, I only have a function. But I do have defined identity. I'm not sure if he's reusing the actual identity defined from before. Now, definition of successor. Well, this is new. Yes, I actually defined it not in the right way, because I defined the successor, right, as if I had a plus. Now, that was a bold assumption on my part because we do not have a plus yet. If you were paying attention. No, we do not have a plus yet. We don't have numbers yet. Certainly we don't have a plus. So how would you define a plus? This is interesting. Definition of a successor. And I remember the successor was defined in like first or the second lecture in structure and interpretation of computer programs, and it was defined simply by, n successor is n plus 1. Successor of n is n plus 1. It was called the increment, I think. They said increment. So the inc of, so it was like the inc of n equals n plus 1, right? I don't think I can even use this. Unexpected equal. Well, I guess you could say inc equals n plus 1. This would work in x, and dec equals n minus 1. So now we have an increment and a decrement. So now you could say inc 1 plus dec 1 is 2. So increment of 1 is 2. Decrement of 1 is 0. So 2 plus 0 is 2. Right. So this kind of example was used in the first or the second lecture of the famous lecture. But this is now, I like this actually even more now. So this is defining, wow. Let's try it out. So the successor, let's make it big and bold. Successor equals, so lambda n, lambda s. So we have two heads and a body now comes in. Oh, these are the booleans that we didn't understand, right? But false is select second. So we have now s false. We do not have a false yet. Right. I should define false at least. Let me quickly define false. False is basically select second. False is if I give you 1, if I give you 2, you give me back the second. This is false. Now we can define our successor equals, so we have two heads, right? N and S. And now S is what? False. N. This is the successor now. Wow. So each time the successor is applied to a number n, it builds a pair function with false first and the original number second. For example, 1 is a successor of 0. Lambda n and the original number second. What does it say here really? Lambda n and lambda s. Okay, s false and 0. We supply it here. Now 0 comes here. Oh, the n number, right. 0 comes into the n place here. We drop the head, we get a lambda s false 0. Similarly, 2, suck 1, lambda s falls, and 1. So same thing, 1 will drop the n head, go inside here, we're going to get lambda s falls 1. S false. Oh, now instead of 1, oh my, instead of 1, we kind of copy this thing because success 1 is this thing. So we need to copy this thing here. Wow. And 3, this is actually 2. And 3, successor of 2. Right, now we get successor of 2 is this. This is the 2. So we need that for the 3, so it will be even longer. This representation enables the definition of a unary function is 0, which returns true if its argument is 0, and false otherwise. Remember that a number is a function with an argument which may be used as a selector for an arbitrary number. Yeah. What's the time? 24 minutes. Yeah, I am actually tired for this now today. This will be it, I think. But it's interesting. We kind of scratched the surface. I kind of do understand what's going on. But I think I need to check the booleans again because it's funny, like there is a conceptual understanding what's going on here. But I see it less and less the far ahead I move, you know, the more I move ahead, it's like I'm becoming more blind and blind. I guess up to a point where I will reach some kind of conceptual wall that I wouldn't be able to understand. So, this is it for today. I guess it was fruitful in a way. And thanks for watching.